Hi, I'm Ananya Bal, and I'll be presenting our work on 3D deformation simulation for vascular tissue with 2D medical imaging. Ultrasound imaging relies on contact forces for acoustic coupling, which causes undesirable tissue deformations. This can affect robotic performance for tasks such as reconstruction and needle insertion. We therefore require methods that estimate 3D tissue deformation. FEM simulations require per-subject tuning, sim-to-real gap reduction, and are not real-time. We therefore motivate learning-based methods that can infer deformations in real time. However, training these requires 3D data that cannot be obtained from ultrasound alone. We have therefore focused on developing a method to leverage 2D ultrasound data for tuning simulation models that can generate reliable 3D deformation data. We use ultrasound and CT images to form volumetric meshes of a medical phantom and a live pig vessel for our pipeline. Additionally, the medium relaying information from the real world to our simulation models is robotic ultrasound. Here, you can view the raw data that went into creating our deformable models. We start by probing the ultrasound phantom at varying forces at different poses and capture ultrasound images through our robot. Using our segmentation model, we obtain ground truth vessel masks. Simultaneously, we define a registered simulation model with varying values of Young's modulus and Poisson's ratio. Once we have simulated deformations, we try to maximize the IOU between ground truth vessel masks and deformed contours from the simulation to obtain optimal material properties. This calibrated model can then be used to churn out more data from different poses and forces. On the left here, we observe an increasing overlap between the vessel contours from the simulation with respect to the real-world data during optimization. On the right, we present a visualization of the growing deformation field in 3D. We are currently investigating using these simulated fields for training force-conditioned 3D flow estimation networks. Thank you.